coronavirus in protein-protein interaction network corresponding to, if I take a look here, right? So I want to show you there's two, the right one corresponding to virus. And this green one corresponds to human proteins, right? So in this graph, we have two types of objects. And the red one, or the red one, is virus protein. The green one, which is the human's protein, right? Can you see? And then, so you can see here we don't care about the interaction between the virus. We care about the interaction between the human and the virus, right? So it means we care about this part a lot, right? So this is the graph. And you think about it, this is the coronavirus with human interaction. And usually people study, the human, people study for another easy produced species more than this one. Corresponding to, people already have a coronavirus with the bat. People have a coronavirus with snake, with this kind of animals. There's more knowledge on this kind of species than the human. So now the question is if we compare two networks, and then we want to say from these two networks, what we can, get some insight. And for example, if some species, right, and the coronavirus on the BAT, the bat, has been well studied, in that case, we can use that information for human study, right? So this is the idea of network alignment. Okay, good so far? It's good? Okay, so it's good or not good? It's okay?
It's good.
Okay, very good. Okay, now I would like to, so this just to answer your question about the network, right? So you can see this is the network, and you can think about you have this kind of network, right? And of course, the interaction will be different. The picture will be different, right? And the network structure will be different. Is clear? So now I would like to, okay, let me save this one. This is for, okay, then I'll create a new file. Okay, good. So I'll put it in the two side. One is the paper side, right? I want to show you the paper at the same time. I want to explain to you. Okay, and based on the paper, usually, for us, for everybody, the second big section is very important for us. Okay, so in your side, you need to focus on this part. This is second section. So now I want to explain what is this alignment, what is algorithm here, right? Okay, so I'm writing here. Okay, so this is about the Spinal, and this is the paper 2, right?
Yes.
Okay, and then so this is about the network alignment, and then first let's say what is the computational problem in this network alignment, right? And then we see that, then after that is we take a look at specific solution of this paper. Okay, and then so this is corresponding to given two graph, right? Just like what we say on the screen, and that is one of the graph, right? So give two graph, and we use this one to represent. And usually we have weight, right? And then we have G2 equal to, let's make it bigger, equal to V2 E2 W2. And use these two graphs, each graph corresponding to one of the protein network, right? Clear? So in this question, it is in this paper, to find a aligned network, aligned graph. The goal is for this paper is to find a aligned graph. And this line graph, and the author claim this line graph name, they denote it as A12, corresponding to alignment graph. And this is equal to V12 and E12. And the author ignore this one. This one in this paper, they ignore. But in your side, you can think about how can you add that. And so I want to explain that, right? First, I give you an example, and then you will see, I will explain this, what is V12, what is E12, right? So I give you an example. And so let's see example. I draw a network. And this is the G1, right? Then I draw another one. And also in this one, I give the label. This is V1, V2, V3, V4, V5, right? And then I draw another graph. I draw the graph in this way. And also I give the variable name, right? I give this one a little bit more, right? And then, so we'll give this one corresponding to U1, U2, U3, U4, U5, U6, right? So this is the G1. Here, I assume all the weight, because in this paper, they ignored weight. So, and let's see, we assume all the weight is 1, right, in this case. In your case, it is, you can think about how do you make sure they can hold for that weight on each edge, right? Here, I assume all this 1, edge weight is 1. So this is the G2. Now, from these two graphs, the author, they want to make another graph. And this graph corresponding to if, I use different color, right? I use this color. For some reason, we find the best mapping, and this one can be mapped. And this one can be mapped. And this one can be mapped, right? And also, for some reason, this one can be mapped, this one can be mapped. And I also would like to make sure they could find this what they supposed to find. This is 182, right? And they want to say the vortex here corresponding to V1, U1, because they are mapped, right? And this is the new node. And they want to make sure what? Make sure that all these mapped pairs from different graph, which corresponding to the new node here. And corresponding to this will be V2 and U2. And this will be V3, U3. And this will be U4, V5. And for me, I want to move this one a little bit down. I want to leave a little more space, right? And then, so I continually explain to you. So this part, this will be V2 and U2, right? And this part will be V5, U6. So this is the new graph. And in this new graph, this is new edge. This is a new edge, right? This is new edge. On this graph is the edge compared to here is different, right? Because this is the edge connected with the vortex in the V12. Can you see? Right? Can you see that? This is this guy, right? This guy. This guy, it is what we would like.
Yes.
Yes, thank you. No, so then so go back to here, right? So now this graph, the new graph, what this paper, they want to make a new graph like that. From these two, they find the best mapping and make the graph like that, right? And this graph consists of the new connection of vertex and also new connection of new edges. And then so they denote, right? Denote V12 as odd, this one, odd. Okay, good. And so claim that as all this VI and UJ. So maybe I put the order a little bit different from paper, but the idea is the same, right? And this is UJ, and all consists of this one, right? And so VI is belong to V1, and UJ belong to V2. Can you see? And also they are mapped, right? They are mapped. The map corresponding to, in this case, they want to find the best, this kind of, this A12. And also E12, Earth, E12 Earth, Earth, yes. So E12 Earth what? So since they need to connect with, the two specific vertex, right? So it corresponding to, let me write it down here. It's corresponding to this, you know what is meaning of this format, right? This corresponding to all the pairs. And each pair, this came from this vertex, this came from this vertex, right? And so this is the condition.
Yes.
Yeah, very good. So then, so we have, we have the vertex, right? And if I draw this corresponding to VI and UJ, and linked with VK with UL, and this one also have this sign, right? So this is the pair they wanted to have. And also this pair satisfied specific condition. The condition here corresponding to the VI, VK belong to V1. And UJ and UL belong to V2. And also VI, the VI go to the, this one should be, yeah, VI, can you see? VI, I go to the VK, which belong to E1. Oh. Okay. So this corresponding to VI go to VK belong to E1, right? And also UJ go to the UL belong to E2. So that is the condition. You see? So this is the formulation, right? This is problem formulation. And this is the example. Now I'm going to the author's method. And the author, what they do, take a look at the algorithm. Go to the page. Let me show you the paper. Go to the page. This one, right? This one. Can you see? So in this paper, yes. So in this paper, they have two big steps. And the big step corresponds to what? Corresponding to, let's see, what is the big step, right? So the first step, step 1, and the also called is course alignment, course grid construction. So this is a coarse grade construction. This is corresponding to what? Corresponding to they also need to find out, take a look at this one, right? Before they recognize the edge connection here, and before they do anything, first thing it is they need to make sure how to align the vertex to vertex, right? They need to decide what is the calculation for each this pair. And the calculation for each pair correspond to this formula, right? I use different color. So calculate the similarity of each pair This is VI and UJ, right? This is what we talk about here, right? Here, right? Take about this one, right? VI, UJ. So they wanted to calculate the similarity of each pair and VI and UJ. They use the formula to represent. Use P to represent. And this is VI, UJ. And so they also think about two vertex, right? And one, this is the VI, this is UJ. And as what we emphasized here, just like this picture, we just want to check for one pair first, right? And this pair V1 have 3 child loads. And corresponding to VI, let's use VK to represent, right? So this is the VK1, this is the VK2, this is the VK3. So this is the VK1, this is the VK2, this is the VK3. We use this one to represent the adjacent vertex of V1, right? And we use this one, I want to use a different color. And this one is UJ, and this is the, for some reason, they have 4 adjacent vertex, right? So this is UL1, this is UL2, this is UL3, UL4. Can you see? Right? So each, this corresponding to this vertex, and they have associated 3 vertex, and this is from the G1, right? This is from G2, and this is from the G1. Okay, and to calculate the similarity, they also think about this similarity not only related to. They use this sign, this is theta, to represent this is kind of a balanced parameter, right? The balancing weight. They use theta and use this one to represent sequence similarity of VI and UJ. But except this one, and they also consider this corresponding sequence side of these two, how similar they are. And then they have a second term, and use this theta to balance the contribution from each side. And so this part corresponding to what is the contribution of the labels to this guy, right? For example, so we see just think about it this way, right? So we have 2 big program, right? Think about one is a chemistry program, one is a computer science program, and Sepla, you could be one of the load here, right? And then so we have another chemical that the people, the department, they also have a student, right? So let's see, let us make Sepla with the leader, right? So Sepla, which will be the VI, and another people in the chemistry is UJ. And VI lead multiple students here, right? For example. And then we want to check, when we check the similarity between the Sepla and Lisa from different departments. First, we check how similar these two could be. And then we also need to check how similar the leadership could be, right? And corresponding to how this, what is the people, he connected, how these connected people similar to, let me draw a picture. So we want to check how similar this one and with this one, how similar they are, right? So when you check the V1, so when you check the contribution of the labels from V1, Vi, and Uj, you may need to consider the adjacent vortex. So this is the point. And such that this is equal to theta and summation of P all the adjacent vortex. This is in the paper they use X, and for us, since we use this VK, we use VK, and this is the UL. We use this one to represent. Can you see? I don't know why it cannot change the. It just not appear. Can you see the screen? Yes?
Oh, yes.
Can you see what I wrote?
This,
I think the internet has a problem.
This VIUJ and...
Yes.
Yeah. You wrote only this VIUJ and it's like VK, UL and all that. This is all vacancy as of now.
Okay. Okay, good.
Yeah.
And then now let's use this one to write. Maybe this one's good. Okay, in my study it is in it just doesn't matter what I wrote. Currently they do not appear. Okay, so this is the formula, and I think maybe because my computer the speed is not too fast. So especially when we have the ResWeb EX, and at the same time we write, since the computer become very busy, and sometimes they cannot give very quick response. Yeah, it just not respond very slowly. Very slowly, yeah. Okay, so let's just see what I can do. Usually in the evening it's better. In the evening, the same not so many people use internet, then it become better. Okay. Okay, can you see? No? So at least now for me, I cannot see. Now in that case, I go to the paper. I want to show you the paper, right? So this formula is the same as the paper.
Oh, okay.
Mm-hmm. It's just what I wrote here, it doesn't appear. It's just they respond very slowly in the computer.
Yeah, I think internet is slow. Yeah.
Yeah. Okay. So let's see what else. Mm-hmm. Okay. So this is correspond. Oh. Okay. Okay, so you can see this is the formula I wanted to show to you. This is supposed to be this one. Can you see? This is
yes.
Xi, Yi, Yj corresponding to adjacent vortex.
Mm-hmm.
and corresponding to adjacent vortex, right? So in that case, and also divided by the degree of this xi and yj. Let's see right now. Yes. So this is the equal to, we consider this two, right? Consider this one, right? Adjacent one, right? So it's summation of P, and this is corresponding to, in this case, in this one, which go to the Vk, this is Vk, right? Vk. And we use this one to represent, this is the Vk prime, right? All this Vk prime here corresponds to what we have, the one of this guy, right? Can you see? And then so this will be UL prime. And then so no, this side, this part, if we move this one a little bit, okay, then so this one corresponding to this side, right? This Vki prime, and which is equal to the adjacent vortex. We use adj to represent the Vi, right? And also keep in mind, because no space, I supposed to write here. Okay, so this is the UL prime belong to adjacent and UJ. Okay, so this is supposed to be here, right? Corresponding to, you do calculation on all this one. And then so after that it is in the I think I still need to move a little bit. Okay, so here the reason it is they wanted to normalize that, and they normalize it the way by divided by degree of Vk prime and Ui prime. So this is divided by degree of Vk prime and times degree. The degree, you know what is degree, right? Degree corresponding to number of adjacent vortex and UL prime. So this one, I think this one should be make it a little bit bigger, so such that you will not be confused. Okay. So this is go to here. And also, this is divided by, in this case, they claim that it is the use specific, use C corresponding to this guy. I think they will be better to use this one to represent. Use V12. This is same as the paper mentioned, and the reason it is the paper they called this V12. Later they say they build the C, right? This C is corresponding to the V12. Okay, they just wanted to make sure this is the changed version of C's changed version. Just be aware of that. Okay, so this is a formula for calculate the similarity of each pair. And then so in this one, very complicated, right? Because especially for this side, because when you calculate the similarity score of Vi and Uj, you consider similarity of the child loads, right? You consider each pair of this kind of child loads. And then so even for each child loads, you say this guy, and they may also have the child loads, right? So this definition is recursive definition. Can you see this recursive definition? Yes, right? This is recursive definition.
Yes.
Yeah, because this P appear in the two sides. This P appear here and also this P appear here. And because think about these loads, they also have its own child. And these loads, they may also have its own child, right? And such that when you do this calculation, you also need to consider the child loss calculation. If this is a tree, then it's easy. You can start from the top, from the bottom, from the leaf, then you go to the top. And now, since it's a graph corresponding to, it may have a cycle. If they have a cycle, give you an example, right? If they have a cycle, for some reason, these have a cycle. And then in that case, the calculation of this guy will be rely on the child loss, also include here, right? And since you do have a cycle, and such that this vertex and also rely on this one, and such that they are influence each other in some way, maybe finally they got balanced. But still, you cannot just use one step to figure out what is the similarity between the VI and UJ. And you want to make sure, let it try, let it see how the labels influence the contribution of the similarity of these two. What is the contribution of the child loads, right? And then you want to check that because they do have a cycle inside. So you want to make sure it is tried many times until they stay in some static version. So this is go to this paper, the algorithm here. I'll go back to here. So then you can see this is the first this step from line 3 through line 14. This corresponding to coarse-grained. Can you see that? So this is coarse-grained, and so initialize this step. Initialize. Let me write it down here. Okay, the algorithm, right? Okay, so the coarse-grained. This is a coarse-grained construction. First step, to initialize P, VI, and UJ. Initialize this one. And in the paper, they mentioned the initialize in the way this is equal to same symbol. Theta, use what I wrote here. And this paper, some place not so, I think it's the same. Yeah, that's good. Okay, this one, and I use the degree difference. This is just one of the way to initialize that. You can even initialize to be each one is 0.5. It's also okay. Let's just say this is the arbitrary method. It's kind of a heuristic method. So 1 plus theta times the sequence similarity of VI and UJ. And for sequence similarity, this is the same as this one is the same as what we talk about. This is the same as what we talk about the sequence alignment. In one of the class, in the face-to-face class, right, we talk about the sequence alignment. And this is the sequence alignment. And they use a specific tool, which is a BLAST. Okay, so they may, in the software, they may pack them together. But this is very typical method. So for this one, you do not need to worry about that. It's just like compare two, a sequence of texts, right? Just like compare two emails, similar as that. You can treat that. And this one, this is just a heuristic method. And this is the degree difference. You can just put everyone to be 0.5. It's okay. And here is just check for the, it's just initialize this one for what? For every pair. For every pair. And every this is VI and UJ. And this is VI belong to V1. And UJ belong to V2, right? So this is the fourth step. This is corresponding to the statement here. The line 4 to 6. Corresponding to this one. Corresponding to the line to here. Right? This is this statement. And then so after that, right? The second step. And the second step used to get a rough idea about this PI, got this one, right? They wanted to say this is the initialization, and this one get the refine or recalculate. This just initialize, right? So let's just say this is the corresponding to calculate PVIUJ based on labels. So this is the step 2. And step 2 corresponding to line, let me write it down. This one corresponding to line 4 to 6. And this one corresponding to line 7 to 7. This is corresponding to the line 7 to 14 in the code, in the algorithm. And this is corresponding to, they need to calculate the PI and VJ, right? And how do you calculate that? So to calculate that, this is very similar to the page rank. And so, they want to check, the previous, because you can see since this recursion, right? And when we do recursion, what they do it is, people want to check the k iteration, and what is the results, what is the pk minus 1 iteration. So corresponding to the, just like take a picture, right? Take a picture of the graph, and then let each this kind of vertex to adjust the data, p based on the labels. Then you get another picture of the graph, right? And so such that they use this one to tell. So corresponding to, this is the k, and this is the k minus 1. And this k corresponding to, maybe I don't need to use k because you have another k, right? So you can treat this one as the t, different time point of let's use t to represent. This is t plus 1, and then this is the t. Okay, so corresponding to, in this case, corresponding to let's say keep them same. This corresponding to different time point, right? Corresponding to corresponding iterations. So in this one, they don't want to use the recursion to do that, and they use iterations. They have different way to convert the recursive solution to the iteration. In this paper, they use this is t plus 1, and this is t. Okay, and so this is the same idea as the paper dimension. To calculate this one based on the labels. Since the labels should calculate data on the PIK, right? PI, VI, and VJ. And such that this procedure maybe go around and around. And finally, you wanted to finally come down to find out that the score got finalized. Okay, so this is calculate the PI and VJ based on labels. So what they do it is they sign initialize. I use this one to represent. You use P1 and equal to what you initialize the P here, right? And the same as, this is the same as the line 8. This is the same as line 8. And then, so after that, it is, you say for every vertex, VI and UJ, and of course, this is belong to V1, right? And this is belong to V2. So you repeat it do this way. So what you do it is, since you need to consider the labels, right? The labels. So the author, they use a very typical way. I use the color represent they came from different graphs. Okay, and then I need to draw this one. Then they will go back to the algorithm. So this one I change to be 3, and this one I change to be 8. Good. So now I put it this one, right? So I move this one mouse to here. When we check this yellow part, we check how similar they are for each pair. If they have 3 nodes, if they have 4 nodes, how many pairs you want to check? How many pairs? 12, right? 12 pairs you want to check. This is corresponding to if I, treat these 2 graphs in this way, right? In this way. I draw here. Or maybe I draw here. Okay, let's make it a little bit smaller and such that you can see clearly. Too small, right? Okay, good. So this is 2 graphs, right? So these 2 graphs, I can change the view in this way. I see this is what I have. I want to use the color. So this is what I have the VI, right? This is what I have and UJ, right? And then so VI, which has the 3 neighbors, and this is the VK1, this is the VK2, this is the VK3, right? And this guy, which has 4 labels, and this is the, I think, this is V. And this is V. And this is V, right? Okay, and then so let's make sure we can change. It's clear? Good, right? So this is the V, this is the V, yeah. And then so I would like to use this color to say this is U, is UL, right? This is UL1, this is UL2, this is UL3, this is UL4, right? And so to compare this children's, so in that case, how many comparison you need to have? So we need to have draw each line from one vertex to another vertex. So this is the alignment. In this paper they call the bipartite graph, and they call this one as the maximum matching, and corresponding to maximum matching. Corresponding to, just like this formula tell you, right? So they need to consider the child. Every time when you take a look at these 2 nodes, how similar they are, except the sequence similarity, you need to check the labels and how these labels can be aligned. And also you go back to here, go back to the previous, the picture we draw, and also wanted to make this graph, right? And in this graph, the yellow line exactly corresponding of one of edges from each graphs. And they want to have exactly 1-to-1 matching. And such that, so to calculate the contribution from the child nodes, and the author make this one. And in this paper, they called this one as the MBG. It called MBG. MBG corresponding to, what is MBG corresponding to? The neighborhood bipartite graph, right? So this is what this is the author name at neighborhood bipartite graph. Let's go to the algorithm and the line 10, right? So this is they make this graph. Can you see that? Corresponding to this one. This is corresponding to MBG. MBG on the VI and UJ. Okay? So they make this guy. They make this guy is not enough. They need to find out how similar they are. What is the best mapping? Because they need to find a one-to-one mapping, right? And such that they were based on the edges, based on the edge weight to decide. So this one corresponding to the P, this one, the weight here corresponding to P, VK1 and UL1, for example, in this case, right? So let's just say, use some way, you find out in this MBG graph, this vertex can be mapped to this guy. And this guy, this VK2, can be mapped to here. Right? I use a different color to represent best matching. This is the best matching.
Professor, I have one doubt.
Yeah.
In this graph, what we do is we will check each pair of VI with all the pairs of UJ, but we map only one pair which has maximum similarities, right?
Yes. So you need to first.
In this is only one-to-one mapping, right? Not one-to-many mapping.
Yes, this is one-to-one mapping.
Mm-hmm. Okay, fine. Yeah, thank you.
Yeah, and then so the worst what they do, they go to here, right? So first construct MBG of VIUJ, right? And after that, find the best mapping. To build this one, just for find the best matching. And put this best matching as in the C. And say it is the best matching results. Okay? It's clear?
Yes, it is clear.
Yeah. So after they find this best matching, now they use this one to compute P, VI, UJ again. And this is the P, VI, UJ corresponding to T. Let's use T to represent, right? T, this one. In this case, T equal to 1, right? And then, so after that, it is, you repeat, you do this one, right? Do this one. And then after the P, you T plus plus. Can you see that? Mm-hmm. So, yeah. So when you build this, when you build this one, you have, this is the T minus 1. This is T minus 1. Based on the previous iteration, you do this calculation, calculate the weight. And then after that, you find the best matching. You go back to here, use this formula, right? Use this formula. Use this, not the formula here. Use this formula, right? Use this formula. You use this formula, do calculation here. If I say this is the formula 1, right? Formula 1. Then, so here, you can compute this one by formula 1. And then, so you calculate this one. And then you T plus 1. Go to the next iteration. Do well. This is the same as the paper mentioned, repeat. Because I do not have big space. I just use do well. It's the same as the repeat and tier, right? And in the paper here, they roughly mention this is enough iteration. Corresponding to there's no change, or the change of in this iteration, you can treat this the whole thing here as the matrix, right? This is the matrix. Can you see the P, VI, and UJ, which is corresponding to one of the value in the matrix, right? This matrix corresponding to V1 to V2. Can you see? This is the mapping for that. So in the very beginning, you initialize this matrix. Then you go to this for loop, right? P is a matrix. P is matrix. Now this is what we mentioned, different iterations corresponding to different time point. The different, the one time, take a look, this P, this similarity between two vertex. Then the next time you go back here again and check the similarity. Go back again and check the similarity based on labels. Okay, so use this one to adjust what is the influence from the labels. Because this is recursion, you really don't know, especially once they do have a cycle in the graphs. You don't know how much influence from the labels could be. Because labels could influence other labels. Maybe you will influence yourself again and again. Right? So, but we don't know. We need to make sure it is. So in this reason, the paper mentioned, let's check and check. Let's repeat this procedure. Can you see that? So in that case,
yes.
So in that case, until now, you finished the big step 1. Then you go to step 2. And step 2 actually was corresponding to refine the calculation. Refine this P, VI and UJ, and use another way to refine. So what did the people do it is, in this paper, now I can go back to review as the 100%. Go to here, right? So the step 2, let's go to step 2. And then, so in that case, what did they do? The first step, so now you already have the matrix, right? You already have the matrix. So you already have this matrix. And this matrix corresponding to the P, what you calculate, P and VI and UJ, right? And corresponding to V1 map to V2. So this row, this column, right? And this one corresponding to the vertex VI, and this column corresponding to UJ, right? Can you see? So this value here, it is similarity score. And this is from the previous step. Finally, you got some stabilized P. Alright, so you use this one. And then, first step A here corresponding to sort odd P, VI, UJ for all, right? For odd this VI and UJ. Corresponding to all this value here, you sort them. So this step 2 corresponding to the algorithm line 16 to 26. This is to go to the second step. And then, so first one, you sort them. And the second step, they started to build this, build the graph, right? So the step is refine this one. At the same time, make the A12, right? The idea is to make A12. So they start to make this A12. Corresponding to, although you got some good P, VI, and UJ, and in this matrix, now they want to extract it, finalize the results. And such as sort this one. After sort this one, they sort this one and put this one. Let's just say this one is saved to SP, right? Because later it use SP. And then so repeat to something and repeat. Now I just same as the paper mentioned, use this repeat. You can also use the do well, right? Do well, same. And so what you do it is you from this SP or this SP or these pairs, right? And so you retrieve the highest because this is the sorting. So you once you sorting, you can DQ, right? DQ, you can use array, you can use the priority queue, right? You can use priority queue, you can use queue. So you DQ, so in the paper they mentioned that is pop. And you pop one specific unlined, this VI and UJ, right? So in that case, it means you pop the best score from here. The pop best unlined VI UJ from SP. Same thing don't appear. Okay. It's just the speed is not so good. So this reason when I move the mouse, move the screen, it appear in this way. Okay. So this is kind of ugly. Okay, and then so you pop this one out. Let's just leave that to save your time, and also have to go. And then so after that it is follow the same procedure, right? You pop this one out. You see this is the best mapping. Now since you wanted to make this A12, and A12 is equal to V12 and E12, and now you want to finalize these graphs. And from what you have all these metrics, you pick up the best aligned in this one, right? For example, you pick up, let's say you pick up this guy, right? You pick up this guy. Once you pick up this guy, you need to decide how to pick up the other guys, right? So what do you do? Still, you check the neighbors, right? Check the neighbors. And when you check the neighbors, and so since this is the vertex-to-vertex mapping as the loads, and such that when you check the neighbors, how many neighbors for Vi, how many neighbors for Vj, Uj, and such that it has the multiplication, right? How many times? So this reason, they also go to here. They also, you can use the loop to do that. It's okay. Or in the paper, they use the repeat. And so it repeat, construct, same as before. Construct this an MBG of V12 and P. So corresponding to, this is what you have the P, right? The whole P here. And though you wanted to construct on this one based on this one you have. You do not, based on, also based on the graphs corresponding this one, right? Corresponding this one. So, once you have this, the file P, and then you see this is the best currently in all this, vertex in the V1, vertex in this Uj, this is the best mapping. So, then in that case, you pick up this one as the seed, right? You use this one as a seed. And then once you use that one as the seed, you reconstruct this MBG. You rebuild that, neighborhood bipartite graph to find the best neighbors for that. So this is called refined procedure. This is a heuristic method. In this method, they do have, you can see that when you run the code, you will see sometimes, it takes time to find the final results. For some case, maybe in the level have final results. Okay. So this algorithm, you can think about how to change that. And so this one repeat construct the MBG corresponding to, this is the, based on the graph here, this is not the regular Vi and Uj. This is the best mapping U and Vj. Then you redo these steps to refine what is the best neighbors for mapping. Now the goal is in order to check what is contribution from neighbors. Now you just check what is the best mapping for the neighbors. It's kind of, BFS. So this one, you can treat them as use BFS to find it out, the whole step here. I wanted to, give the idea. So this is use the BFS to build, to help build the A12. It's starting from, because it's sorted, right? And it's starting from this one, you can treat them as priority queue. And you starting from this sorted, this one, pick up the maximum mapping and use this mapping as the seed. Use this one as the seed. Use this one as the seed to find the neighbors, right? That always think about this one. It is they're trying to mine the map the neighbors. Best map of neighbors. Okay, and then so after that it is for the same steps. They this one, the paper code is constructor, contributor. This is corresponding to, we talk about best mapping. Best matching or best mapping. It's the same thing. or matching. Corresponding to the steps here. Corresponding to the steps here. It's clear? Let me know if you have any question or maybe it's too fast. So you find the best mapping. And then so this in the paper, then they call it is the best it's called C. It's called C. And so it's construct the best mapping, okay? And then so after you construct the best mapping, then they say then if some edges which is not in the for example here, right? So in this one we see that this purple line corresponding to the C, corresponding to the best matching, right? And then some of this kind of green line, which is the possible matching, but not the best one. And in the paper they say swap improvements for each neighborhood graph edge not in the C, not in the C. This step you check this step. In the paper they do not exactly mention what does mean swap improvement. In my mind, corresponding to based on this one, you readjust this P. This one corresponding to readjust this P. The P matrix. Readjust this P based on what you built this based on MBG. Right? So you rechange this value on this P. At the same time, you extract the best mapping. When you extract the best mapping, in the way you already build the best pair. This is the VI and UJ, right? And based on this step, you find out the best matching. And this best matching here is belong to this C. What you created this C, right? This is what you find the best matching here. Corresponding to, you find out in each this rectangle corresponding to, based on previous picture, it will similar to, for example, VK1, which map to UL2, for example. And you have a VK2 map to UL1. And you have a VK3 map to UL4. And so this is the best matching from this graph. From this graph here. For example, right? Maybe I give the label, not the exact matching, but this is the idea. And so this step, this the whole step here. This the whole step here. This is the whole step here, and this is until no need, no new C, right? And then so in that case, this is to create this guy, this level. This one create this level. And then once you create this one, it will be increased, put it back to this what we have the V12, right? Then after that it is you go back to here again and again, right? So until. So in this case you can say this is the BFS. And later they use this this kind of vertex pair you have, and to redo adjustment, you want to check what is the next best mapping for here. And in such way, you use this procedure in each iteration, repeat this iteration used to calculate for one level of this A12, right? So in the very beginning here, and one iteration, you get this one. And then the later iteration, you will get the second level, which is the best matching for the child of this guy. For the child of this guy and for child of this guy, right? And then so you propagate it out. Finally, you build this A12. This is the idea of this algorithm. Okay, I think we finished that. It's corresponding to this paper mentioned, just like here. Okay, and then so do you have question?
No, yes, okay. This is fine.
Okay, and then so